Welcome to this third and final recorded video for the homework notebook for the fourth computational module. So here I will go over a quick but useful introduction to differentiating functions defined in terms of integrals, and then the last problems for this notebook. Before we get to our last problem, we show how to integrate a parameterized function using the quad function, which was also shown in the lecture notebook, the Part B lecture notebook of this content module in the course. And then we will show how to differentiate the result with respect to its parameters. This will greatly simplify the last problem of this assignment, and it is also an important thing to understand in general in terms of being able to do it and use it in code. The content is borrowed and edited from the official documentation, which is found here. So I am going to import the quad function from the integrate subpackage of SciPy, and now I'm going to consider a family of parameterized exponentials. So here I define a function f that I want to integrate for x values in L. I'm using L here, ELL, to make it, because if you just have the L, it looks too much like a 1. I'm going to have that as the parameter that is affecting the shape of the function. So then I return the exponential. I'm using NumPy to compute the exponential of x times L, and then that gets multiplied to x minus 2 raised to the third power. Now suppose we want to know what the various integrals are of this function on the interval -1 to 1 as a function of various L values. Then we use the quad function as follows. I create a lambda function of L, much like how I created a lambda function of R for surface area where I called the center difference approximation to a function. Well, now L is different values of L determine different values of the integral, which I use I to store as the function for the integral. And then I use the quad function to compute the integral of f from -1 to 1, and I pass as an argument the L parameter. That's it. That's the format you would use. And then again, I've appended that 0 at the end, as is discussed in the lecture notebook, so I can just return the approximate integral value and not worry about the approximate error in that approximate integral value. So when I return that, I now plot the function I as a function of L. So I create my figure. I say the number of L values I care about. I have them go from 0.1 to 2, and I use that number of L's, which I set as 100. You can vary that. And then I create an array of zeros that I populate with these integral values. These are my i's. These are my integrals, so I call them i's. And for each I and the number of computations I want, I compute that integral function on that particular L value, which is taken from the array, the ith value of L in that array. And then I just plot the result. I plot the i's versus the L's. And so there you have it. This is showing the integral of the function f. Now I estimate the derivative of that function. Well, I create another lambda function. di dl, the approximation to the derivative of I with respect to L, is given by a lambda function, where again I use the center difference function method within the differences module. So this has all been imported up above in the code. And then I pass it the function I, the array of L values that I want to approximate the derivative on, and then h. So let's talk about what's going on here. This is taking the derivative of an I function, which is defined in terms of an integral using the quad function, and I'm differentiating it with respect to the L value. And I'm using h to be 0.001 to describe the step size, how much I'm perturbing these L values. But in code, it's not too complicated to write that. And now I just use these twin axes, like what I showed before with the surface area plot in problem 2, to show you the plot of this function, which is I of L, and the plot of the derivative, which is in red. And you see, again, I show 0 here, that we cross 0 with the derivative approximately where the function, where the integral is maximized. So you can play with this on your own. I just said this part about the above plot. A suggested sanity check for you before attempting this final problem is to apply various root finding algorithms. You can do brute force, bisection, and so on that we have seen in this notebook to estimate the L value that makes di dl equal to 0 and plot the results to see that this is where the integral as a function of L achieves its maximum. Now for problem 5. Let us optimize our profit. So some motivation. Recall, you are the world's best pasta sauce maker, and you have optimized dimensions for your 1 liter size jars of sauce to minimize your cost per jar. But you still need to create these jars. You still need to hire and train the workers that package these jars. And you still need to invest in the equipment, warehouse space, and delivery fleet for your business. Oh, and you need to hire salespersons, pay for marketing, and on it goes. It is not only a lot of work building and running a business, it is also expensive. Unless you were lucky enough to inherit millions of dollars, you probably need to get a business loan to help finance your dream of dominating the competitive world of pasta sauce making. What size loan should you get? It may seem like you should just get the largest loan you possibly can. After all, a larger loan will allow you to rent a larger warehouse, purchase more equipment and materials to manufacture the jars and sauce, and hire and train more workers. While this sounds great, building a business takes time. The longer it takes to set up your business will mean you are spending a lot of money before you're making significant money. Subsequently, you may not start to turn a profit for a longer period of time. Moreover, larger loans will often come with bigger interest rates and significantly larger quarterly payments on the loan. In the end, you may run out of money if you try to make everything too big initially. What happens then? Well, your lenders may take over your business and sell it to someone else who becomes the owner of your IP, your intellectual property, meaning your special pasta sauce recipe, and maybe even come after your personal assets if you put them up as collateral, if you had to provide a personal guarantee on the loan. Excuse me. In the end, getting the right loan amount and following a strategic plan based on a certain amount of the loan is perhaps not as straightforward a problem as it may seem. So let's define the problem. Suppose you were qualified for loan amounts between $500,000 to $1 million, assuming US currency. Let that script L denote the loan amount in units of $1 million US, which means that the loan amount L is something between 0.5 to 1 in units of millions of US dollars. Let capital M of T, parameterized by L, again in units of $1 million US, denote a model for your projected net cash flow at time T, where T is in units of days, if you follow a business development plan based on a loan size of L. Assume the model is only valid for 90 days, the first fiscal quarter of your business. That's how far you've projected out based on your loan amounts you might get, how you might pursue using the loan amount to build your business, and that's how you build your model M. If M is greater than 0, then you are making money at time T. If M is less than 0, then you are losing money at time T. So M is your money model as a function of time, and it's parameterized by L. The function changes for different loan amounts. The total amount of money you have made or lost over the first 90 days is the integral of that money model over the interval 0 to 90. So the integral over the interval 0 to 90 of the money function. And this creates T of L. This looks much like our integral function of L for a function f that we did above, right? So that it looks a lot like this. Your problem is now clear. Optimize T of L over the interval 0.5 to 1. Your job is to do the following. Use the function money that computes M of T with a semicolon L here, which is just a parenthesis here. I'll put a space there to make it look a little nicer. In the code cell below to determine what the optimal loan size should be. You are given this function, but you still need to compute T of L and optimize it over 0.5 to 1. This is much like the function I, capital I, of L that we had above. And notice here I'm just using L. I'm not writing out like that, L like that. Make sure to put comments in your code and provide useful annotated graphs and illustration of results and interpret results in markdown cells. So again, your job, use the money function here that computes this model. I've made this model here to produce some interesting behavior to determine what the optimal loan size should be. And you need to do, how do you do that? Well, go look at problems 2 and 3 and how we optimized surface area or cost, and then also look at what we did here with this plotting to find where the derivative was approximately equal to 0, which is where we maximized this. So those are all some really big hints. The amount of code you have to write is actually not too much. And you can copy and paste a lot of what you have above. You just need to make the proper edits. Copying and pasting does lead to a lot of errors, but if you carefully edit and think about what you have to write, it should hopefully not take too long. So that's it. That's the end of this assignment. Thanks for listening.